survive if you are swift. The maximum speed with which a mammal can escape an unpleasant situation depends on complex biochemical relationships between mass, muscle strength, and metabolism. The maximum speed with which the most rapidly traveling entity in the universe can travel is that exhibited by particles that have no mass at all, such as particles of light, known as photons. The maximum speed can be given very precisely as 299,792,458 meters per second, equivalent to 186,282 miles per second, which is almost approaching 1,000,000 times faster than the speed of sound in air. If I could travel at the speed of light, I would be able to travel from my home in the UK to Australia in 1/14 of a second, barely time to blink. Light travelling from our nearest star, the Sun, takes just 8 minutes to travel to us. From our outermost planet, Neptune, it's a journey time of just a few hours for a photon. We say that the Sun is 8 light minutes away from Earth, and that Neptune is a few light hours away from us. This has the interesting consequence that if the Sun stopped shining, or if Neptune suddenly turned purple, no one on Earth could find out about such important information for 8 minutes or a few hours respectively. Now let's consider how fast light can travel from even more immensely distant points in space back to Earth. The Milky Way, the galaxy in which our solar system resides, is a few 100,000 light-years across. This means that light takes a few 100,000 years to travel from one side of the galaxy to the other. The Fornax cluster is the nearest cluster of galaxies to the local group of galaxies, of which the Milky Way is a significant member, and is hundreds of millions of light-years away from us. Thus, an observer on a planet orbiting a star in a galaxy within the Fornax cluster looking back to Earth right now might, if equipped with appropriate instrumentation, see dinosaurs lumbering around on Earth. However, it is only the mind-boggling vastness of the universe that makes the motion of light look sluggish and time-consuming. The role of the speed of light as a mandatory upper limit has an intriguing effect when we start to consider how to launch rockets into space. Escape velocity. If we wish to launch a rocket into space, but its launch speed is too slow, then the rocket will have insufficient kinetic energy to break free from the Earth's gravitational field. However, if the rocket has just enough speed to escape the gravitational pull of the Earth, we say it has reached its escape velocity. The escape velocity of a rocket from a massive object such as a planet is larger the more massive the planet is, and larger the closer the rocket is to the center of mass of the planet. The escape velocity, v subscript esc, is written as v subscript esc equals the square root of 2gm over r, where m is the mass of the planet, and r is the separation of the rocket from the planet's center mass, and g is the constant of nature, known as Newton's gravitational constant. Gravity always acts so that it pulls the rocket towards the center of the planet or star in question, towards a point known as the center of mass. However, the value of the escape velocity is completely independent of the mass of the rocket. Thus, the escape velocity of a rocket at Cape Canaveral, some 6,400 kilometers away from the center of mass of planet Earth, takes the same value, just over 11 kilometers per second, or approximately 34 times the speed of sound, which may be written as Mach 34, irrespective of whether its internal payload is a few feathers or several grand pianos. Now suppose we could shrink the entire mass of planet Earth so that it occupies a much smaller volume. Let's say that its radius becomes 1/4 of its current value. If the rocket was launched at a distance of 6,400 kilometers away from the center of mass, its escape velocity would remain the same. However, if it relocated to the new surface of the shrunken Earth,